Hello everyone, welcome back. This is Mr. Hussein Mwasapi, and in today's video we'll be looking at what is known as a vector addition. So this vector addition is basically just focused on two dimension, whereby we'll only be focusing on the x and y axis. Be mindful of that. Remember, the x is simply the I, while the y is the j components. All right. Now, before we get to it, I would like to subscribe and like the video. All right, let's get to it. Now, whenever we're talking about vector addition, basically what we're trying to ask ourselves is that if I was given some vectors, can I find one vector that represents them all? Now, this vector that represents them all is called the resultant vector. Let's not forget that. So, given multiple vectors, for instance, a force, there will always exist a single vector, like a force I was trying to give an example of, that represents them all. And that single vector is what we're calling the resultant vector. Let's not forget. Now, our main focus is the method that is regarded to be the Cartesian method. So the method we're going to be using, it's not the only method we have, but it's the first method that we're going to use. This method is quite important because it helps you solve a bunch of questions. So it's the Cartesian, I don't know how most of you prefer to pronounce it, method. All right, so in a schematic way, let's say you have a pin support there, and then you have multiple vectors. Let's say force 1, you have force 2, all these are vectors. You also have like force 3, or even force 4 there. You can have so many vectors at one particular point. Now, there should always be one force that represents them all, that represents all these. Now, that single force is what we're calling the resultant force. I call it Fr. Now, if you want, you can always put your y-axis. You can assume this is the y, and then you can just make up an x-axis like that. Same thing here. You can always draw a plane like that. I'll call this the y, then I'll call this the x. So this is what I'm trying to highlight. So there will always be a single force that will represent a lot of forces, or let me say a single vector that represents a multitude of vectors, and that vector is called the resultant. To find the magnitude of the resultant, we use the same procedure. Magnitude is equal to the root of the summation of the forces in the I squared plus the summation of all the forces in the j component, so it's the I component squared, like that, and you'll find your magnitude. Same thing with the direction. The direction will always be the tan inverse of the absolute sum of the components in the j over sum of the components in the I, like that. And after that, you consider the quadrant in which the resultant falls under. All right, so with this said, I would love us to look at an example that will basically help us highlight what we're trying to emphasize. All right, let's look at some problems. Okay, so let's start with the first problem. We're being told to say, okay, find the magnitude, which is the size, as we all know, magnitude, and direction, which is theta, of the resultant. Remember, that single force represents the magnitude of forces. All right, like that. So let's say our equation we're having something like this. So pin support. Then let me create an axis. This is our y. Then we have our x, like that. So let's say we have one of the forces. Let's call this one force 2, which is 25 newtons. And it's measured at an angle of, let's give it 30 degrees. And then let's also bring out another one. Let's call this force 1. Let's say this has a magnitude of 40 newtons. And it has an angle of 45 degrees. Alright, so because all these forces are being connected at one point, their tails are connected at the same point, these forces or vectors to say, we can regard them to be concurrent vectors because they're all coming from one point. Okay, so let's now look for that single force because I've been asked to find the magnitude and the direction. So let me just change the color so I can basically understand it clearly. Alright, so solutions. So all we have to do is to resolve these components. Let's follow the steps. Basically, let's have steps. Step 1, what are we supposed to do? Let's resolve each vector into its components. Alright, let's start with vector 1, which is force 1. I know, but at this time, you're supposed to be adequate with how to resolve forces into their components or vectors into their components. But if you haven't, if you're not familiar with it, you can always check out my video that I made on resolving forces or vectors into their components. Then you can get back to this video. Alright, let's resolve. So for F1, remember it's going in this direction, in the negative I, then it's going in the negative, then going in the positive. So remember where the angle points, that's why you have sine. So we're going to have minus 40 cos 45, that is in the I, then plus 40 sine 45 in the J. If we calculate that, if we compute it, we end up having minus 28.28427125, that's in the I, plus 28.28427125 in the J. Alright, so if I round this off correct to 2 decimal places, then my components in the F1 will be minus 28.28, that's in the I, then plus 28.28 in the J. So these are the components for F1. Then moving on to F2, I'll do the same. I'll go in this direction, in the positive X, then in the positive what? Y. So what I'll be having is, remember the magnitude is 25, so I'll be having 25 cos 30, that's in the I. Then we'll have what next? Yes, 25 sine 30 in the J. Then if we compute this on our calculators, we'll have 21.65063.509, that's in the I, plus 12.5 in the J. Rounding this off to 2 decimal places, we have F2 being equal to 21.65, that's in the I, plus 12.5, you can just write 0.550 in the J. And these are our components. Then at this point, we have resolved all the vectors we're having in that system. So now, what we're going to do is, since we're using the scalar approach, for the scalar approach, let me just give you a quick review. So it's like, if we're using the scalar approach, we're having something like VR in the X will always be like the sum of, all the I components from a particular point in the VR of the X. And then this is the resultant in the X. Then the resultant in the Y will be like the sum of the J's, so from 1, then ending to some number N, then V, J in the Y. So it's like, this is the approach we're using. Yeah, but basically, I don't really want to confuse you guys. Basically, let's just use this method. It's much easier, but all we're doing is literally involved in this. It's like what putting up this. This is just put in a series way, but we'll get a hang of it with time. All right. Now let's move on to the second point, or second step. Sorry, step 2. sum up the I components and J components. Alright, so if I sum up, the sum of the forces in the I will be minus 28.28, this guy here, and I'll say plus this guy there. This will be 21.65, and this will give me minus 6.63 in the I. Then I'll sum up the forces in the J. This will be, I get this number there, which is 28.28, plus that number there, which is 12.50, and I'll be getting 40.78, that's in the J. So now that we've summed up our forces, remember that the resultant is always equal to the sum with the forces in the I plus the sum with the forces in the J. Therefore, the force resultant is equal to minus 6.63 in the I plus 40.78 in the J. These are the components of the resultant. Now, all we have to do next is now, since we've written down the components, we now just have to, the last step, which is 3, find the magnitude. So finding the magnitude, remember, it will be in this manner. The root of the sum of the forces in the I, that's going to be squared, plus sum of the forces in the J, and that's going to be squared. So the resultant will basically be, you get minus 6.63 squared plus 40.78 squared. So if you do your computation rightly, you'd find that this will come out to be 41.31543658. Alright, so now we're basically going to be rounding off our values, correct, two decimal places. So this will be 41.32. Remember, our units are newtons of the components that we have, and not really just the components, but those single forces we're having, or vectors to be precise. So it's going to be newtons. Now we have to find the direction. So theta is equal to the tan inverse, like I said, should be the magnitude of the sum of the J components over the sum of the I components. So we're having tan inverse of, in the J we have 40.78, then we have 6.63. So we're having a value, theta, being equivalent to 505. Therefore, rounded off to decimal places, you have 80.77 degrees. Now, we can't really conclude that this is the final answer. Check the position of the sum of the components in the I and the J. So if you do up the plane, you'd find that the I is in the negative axis, while the J is in the positive. So you are playing around the second quadrant. So in the second quadrant, you expect theta to be equivalent to 180 minus theta prime. So I'll call this theta prime. So theta is equal to 180 minus 80.77. Therefore, our final direction, which is equivalent to the resultant, will be 99.23 degrees. And that's basically our answer. So I can always draw up a simple triangle to help you understand what's going on. So I'm having like the sum of the forces in the y here and the sum of the forces in the x, and this is where the resultant comes in. And the resultant is the hypotenuse. Alright, let's move on to the second example. Now, in the second example, what I want us to look at is basically a different type of problem. It's going to be a bit tedious, but with practice, we'll understand it. Let's say we have a support there. Let me put it somewhere downwards there. So let's say we have a pin support like that, a pin support, and then I'll put the vectors in a different color. Let me put the axis, the x, and this is basically the y. So I'll use red to represent my force vectors. I'm having one here, which is, let me call this force 3, which is 30 kilonewtons. Then I'm also having another force there in the x, and I'll call this F2, and this one should be equivalent to 25 kilonewtons. They're all meeting up to that point. The tails are joining that point. Then I'm also having one in the y. Then I'll call this F1, will be equivalent to 40 kilonewtons. Then I also bring up another one. Now let's make it a bit interesting. This one will be coming into the pin like that. And let's put this at an angle of, no, let's not use 60, let's use 45 degrees. Okay, so let me call this one force 4. And let's give it, this is 50 kilonewtons. All right, like that. Okay, so we have 4 vectors, and now we want to find. Let me give you more information about force. Let's do this. Let's use. Sometimes bring these type of problems. 4-3. Let me just call it 4-3 for now. Okay, so you have 4 vectors, and you want to find one vector that represents them all. So we're going to use the steps, the same steps. So step 1, break up the vectors into their components. Let's break them up. Break up the vectors into their components. All right, so we'll start with F1. Now, if you look at F1 is only acting in the y. So it's only having a j component and doesn't have an x component. So it's 0 in the I plus 40 in the j. Those are the components for F1. And then looking at F2, so we have for F1. For F2, it's basically the same idea. It's acting along the x-axis, so it doesn't have a j component, it only has an I component. So it's 25 in the I plus 0 in the j. So those are the components. Remember, all vectors acting along the coordinate, which is the x or y, will only have the coordinate value. So if my vector is only acting in the y, I'll just have it in the y. I won't have it in the x. If it's only acting in the x, I only have the x component and I won't have the y component. If it was at all acting in this direction, I'll have a vector just in that direction, but we don't have it in that direction, but just food for thought. Then we also have to resolve F3. Now F3, as you can see, you have this triangle right there. Let's change the color. We have this triangle here, but we're trying to move in this direction. For F3, if at all we had an angle here, which is equivalent to the angle there, so theta here is the same as theta there. Okay, so if at all I had theta here, I will move in the positive x, then the positive what? Y. Now, let us understand something. This 4, be mindful, it's a right angle triangle, so it's pointing at the hypotenuse. So this straight line is a hype. Then the angle is pointing at the opposite, and what you have here is an adjacent. So using the trig ratios, SOHCAHTOA, we know that if at all I needed to find the component acting in the I here, it's going to be the magnitude, which is 30, then it's going to be cos theta in the I, then I'll be going upwards like that, which will be plus 30 sine theta in the j. Now let's find the values of cos theta and sine theta. Now let's be mindful that the triangle that we have is a bit incomplete. We only have 4 and 5. Sorry, 4 and 3. So we can find x there by using the Pythagoras theorem, where we know that the sum of the squares of the short sides is always equal to the hypotenuse. So which means that x squared is equal to 4 squared plus 3 squared. If I root that, I have x being equivalent to the root of 4 squared plus 3 squared, which will give me x being equal to 5. So it's a 3, 4, 5 triangle. So that's 5, that's there. So we know the hypotenuse is now 5. So let's try and find the value of sine. So from the trig ratios, sine theta is always equal to the opposite, and the opposite here is 3. So we have the opposite 3 over the hype, which is 5. Then cos theta is always equal to the what? Adjacent, which is 4, over the what? Hypotenuse, which is 5. So these are the values that represent the cos theta and sine theta. But if you want, you can always find the angle here, theta. If you find the angle, you'd find that if you do some math at your own free time, you find that theta is equivalent to 36.87. So if you try and resolve, you do cos 36.87 times 30, you'd find the same answer as one doing exactly what we're doing. So F3 is equal to 30 times cos theta is 4 over 5, that's in the I, plus 30 sine theta is 3 over what? 5, that's in the J. So it's one and the same thing. If you do cos theta, cos 36.87, you get 4 over 5. Yeah, if you want, you can just, if you have your calculators with you right now, you can always just try to punch it and see if it's correct. You'll be getting something like 0.799 something, and then if you do 4 divided by 5, you get something that is rounded off, like the 0.8. So basically you're doing the same thing, but in an easier way. So I prefer doing this using the 3, 4, 5 triangle. I feel like it's much easier. But if you're comfortable with the where you find theta, you can always find theta and plug and chug. Alright, so F3 is going to have the following. So F3, if you compute this, 30 times 4 over 5, you'll get 24 in the I, plus 30 times 3 over 5 will be 18 in the J. And these will be the components for force 3. Change the color and do have the different one. Let's look at the last vector, which is force 4. So force 4 is at an angle of 45 degrees. So we know we'll be going the negative x like that, then the positive y. The magnitude is 50. Alright, so this will be minus 50 cos of we have minus 50, then we have cos 45 in the I. No. If you look at the direction, sorry, look at the way it's moving. It's not really the arrow, the tail, the arrow isn't pointing in this direction. It's pointing in the other direction. I almost made a mistake. So follow the direction. You're trying to move from the tail going to the what? To the head. So you go downwards in the y. So you go negative in the y, then positive in the x. So you're moving negative in the j, then positive in the I. I hope you're clear on that. So it's going to be minus 50 since you're moving negative in the, remember, negative in the j. So minus 50, remember the angle is pointing this side, so you expect to have sine here. So you're going to have minus 50 sine 45, that's in the j. Then you have positive in this direction there. Then you have plus 50 cos 45 in the what? In the I. Then after that, you can just compute this, and all you have is minus 35.35533,906. That's in the J, plus 35.35533,906 in the I. If you round them off to the decimal places, you'll be having minus 35.36 in the j plus 35.36 in the I. If you want, you can push in the I first, then the j later, and you have 35.36 in the I, then minus 35.36 in the j. Like that. And these are the components of all the vectors that we have. Alright, so you can write them down I hope you're writing down most of the points that I'm actually highlighting so that you can move with me. Alright, so the next step, put it here, is simply step 2, where I have to sum up all the components. That's in the I and the j. So the sum of the components in the I, remember we need to find f1 in the I plus f2 in the I plus f3 in the I, since we're having 4 of them, so we say plus f4 in the I. So all these are vectors like that. So sum of the forces in the I is equal to, so I hat like that, is equal to, we're having 0 plus 25 plus 24 plus 35.36, and this will give us 84.36 in the I. Then we sum up the forces in the j. Remember, we have 4 of them in the j, 1 plus f2 in the j plus f3 in the j plus f4 in the j. So sum of the forces in the j is equal to 40 plus 0 plus 18, then we're having a minus 35.36, and we have 22.64 in the j. After that, the next step is to write the components of the resultant vector. Alright, so the components will basically be the sums that we have found. So we say force resultant is equal to 84.36 in the I plus 22.64 in the j. Then basically once we have found this, we now have to just find the magnitude. Then now we say find magnitude. So the magnitude will basically be this, the root of 84.36 squared plus 22.64 squared, and you get your resultant to be equal to, if you compute this rightly, you have 87.34517273. If you round this off to 2 decimal places, you have 87.35. Remember, the units that we are having are kilonewtons, so those are the units we have. Then finally, all we have to do is to find the direction. The direction is theta being equal to tan inverse of the magnitude of the sum of the forces in the y. So that's being the j component over some of the forces in the I component. So we're having tan inverse of 22.64 over 84.36. So theta will be 15.02268741 degrees. Round it off to 2 decimal places, theta is 15.02 degrees. Now if you check the position of the resultant, you'd find that this is positive and that's positive. So it's positive there and positive there, so it's in the first quadrant. In the first quadrant, we'll just take the angle the way it is. Alright, thanks for watching. I know mostly at first glance, you might not get it right, but with a little bit of practice, you'll get a hang of it. Remember, my name is Mr. Hussein Mwasapi. Remember as well that small progress is better than no progress. If you have any queries, you can always reach me on WhatsApp on the number 077 1495252. Remember to strategize before you become a statistic, and let's try and push for that A+.